We normally think of the power grid as a highly predictable machine governed by clean math. We've seen how phenomena like the Ferranti effect, where voltage rises at the end of a long, lightly loaded transmission line, follow strict, manageable rules of physics. But under specific conditions, those equations lose their predictive power. The clean 60 Hz sine wave starts warping into a non-periodic, erratic surge that follows different, nonlinear rules. Engineers call this phenomenon ferroresonance. When a standard electrical fault occurs, the system is designed to trip and clear the issue in a fraction of a second. Ferroresonance behaves differently. It is an undamped transient that actively feeds on its own energy, locking the grid into a cycle that refuses to die out naturally. To trigger this event, two specific components of the grid have to interact. First, you have the capacitance of the transmission cables, which naturally store electrical charge. Second, you have the inductance of the transformer's magnetic iron core. In a normal state of electrical resonance, these two components form a balanced partnership. Energy trades back and forth between the cable's capacitance and the transformer's inductance in a smooth, predictable rhythm. The problem starts when the iron core of the transformer is pushed past its magnetic capacity. The core hits a hard physical limit. In engineering, we say the core has reached nonlinear saturation. Once that saturation point is reached, the physics of the transformer shift. Its ability to oppose changes in current, its inductance, plummets. Because the transformer's inductance is no longer a fixed number, the smooth energy exchange shifts. The circuit enters a state where the voltage and current are no longer governed by a stable, linear balance. A standard linear resonance behaves like a tuning fork. It rings at one clean frequency. Ferroresonance produces temporary overvoltages, characterized by erratic jumps across multiple frequencies, creating a distorted wave. When the transformer core saturates and its inductance drops, the flow of current surges. This sudden shift forces the voltage across the components to spike. That resulting high voltage immediately pushes the transformer core even deeper into saturation. This triggers another shift in inductance, which causes another voltage surge, speeding up the cycle into a runaway state. Because the saturated transformer continuously injects its own erratic excitation energy back into the circuit, it creates a self-sustaining feedback loop. Normal grid dampening mechanisms are essentially powerless to stop it. Fortunately, you rarely see this happen on a typical day. Ferroresonance demands a specific set of environmental and operational factors aligning all at once. The first requirement is an unloaded or very lightly loaded transformer that remains connected to a system with high capacitance. A long underground transmission cable is a prime example of this kind of capacitive source. The second requirement is a sudden disruption to the circuit, like a single-phase switching event. If a breaker opens on one or two phases, it isolates the unloaded transformer while keeping it electrically tied to that long capacitive cable. That momentary switching action is the final catalyst. It injects an initial transient jolt into the isolated pocket of the grid, providing the push needed to knock the unloaded transformer core right into saturation. For grid planners, this highlights a specific risk. A major instability can emerge solely from the operational alignment of entirely intact hardware. Once ferroresonance takes hold, the resulting temporary overvoltages can last for seconds, or even minutes, inflicting stress on the local grid infrastructure. The unpredictable frequencies and sustained high currents generate intense heat inside the transformer. This thermal stress degrades the insulation and warps the metallic core. Making matters worse, the distorted shape of the waveform can confuse standard protective relays. These safety devices rely on clean, predictable signals to know when to trip, meaning ferroresonance can effectively blind them, leaving the circuit live. Left unchecked, this thermal runaway ruins substation transformers and destroys surge arresters, leading to prolonged, widespread blackouts. This is why engineers treat this transient with such caution. It turns the grid's own natural energy storage against its most expensive hardware, bypassing the standard safety nets designed to protect them. To stop the destruction, operators have to actively break the mathematical loop and force the electrical parameters back into a stable state. The best defense is strictly operational. Grid planners design careful three-phase switching sequences to guarantee an unloaded transformer is never left isolated in an energized, highly capacitive circuit to begin with. As we can see in this circuit diagram, when specific system designs make operational prevention impossible, engineers install physical mitigations. A control unit can deploy a reactor and thyristor setup to act as a damping mechanism. By introducing intentional resistance, this setup bleeds off the trapped energy. It drains the excess excitation current, pulling the transformer out of saturation and forcing it back into normal, linear behavior. The modern power grid operates smoothly only through this kind of precise vigilance. We maintain stability by ensuring the volatile magnetic limits of our hardware are never allowed to freely interact with the capacitance of the network.